So welcome to the lecture number 17 of peer-to-peer networks MOOC. In this lecture, we will be looking at the resilience of key value pair storage. In a DHT network. So in the previous lecture, we had looked at that how a source, when is injecting into a DHT network a key value pair, he actually can take key and then actually define that key copy 1 and compute the hash of this from their one hash ID. And he can also compute another hash ID by assuming there is going to be key copy 2 and from there get another hash ID, and that's the way we can actually have multiple root nodes for the same key value. So multiple root nodes will be maintaining same key value pair, and that time we had actually talked about that it will be either key value which will be there, or there can be hash ID of the hash value of the content. So this will be used as a key for the content, or we can define the keys and the content will be there with respect to this. Similarly for this also, again key we will be finding out the hash ID from here by doing the hashing, and this hash ID, whichever is the root node, will be maintaining the value. So we can actually have multiple root nodes and they can monitor each other and they can keep on republishing the entries if any node dies off. So that was a parallel thing. There is another possibility which we can explore. We call it a serial replication. So this resilience is coming because of the serialization. Essentially, we are not going to maintain copy 1, copy 2. So whatever the key value which is there, so I want to store it. I will take the key, compute the hash of this. As a consequence, I will get a hash ID. And I will use this hash ID to find out the root. I will actually send a publish message. So this will ultimately turn up to at the root node where the key and value pair has to be stored. So whenever somebody wants to search, again he will do the same procedure, make a query here. But the problem is this root node can die off. So how this actually is going to be recovered? So we started with this question last time. So the way this can actually be handled is this root node. This root node can now find out among his neighbors. There are actually two possibilities. One is it somehow knows that if this node dies off, there will be some other node who will become the root. So if I call it a root, 0th root, this I can call as a first root. Even this both dies off, then there will be third node who will become the third node who will become the root. I can call it 0th root, first root, second root, and so on. So I can actually have, in the same way I can have kth root also. Okay, this R3. So what I can do is the first copy comes here. This guy actually somehow, if it can figure out, it can maintain the copies at all these places. So it can maintain k copies if it wishes. So whenever a root node dies off, automatically the query will go to the another place where the key value pair will always be there. So I can actually maintain k copies for each actually key value pair. That could be one possible state way of handling the situation. Now this actually can be very easily done if it is a CORD kind of system. So in fact, originally when we were implementing Brihaspati and we were thinking of CORD, we thought this could be a good possible way of doing the things. So we started with this, but later on we actually have changed it because we are using a different algorithm, not the CORD. So what happens in a chord? So chord is all nodes are arranged in a ring. Okay, and it's a asymmetric distance which we are actually following. If the hash ID is here at this moment, then whoever is the next node, whoever is the closest node from hash to the node ID. So whichever has the least distance, so this guy will become the root node in this case. But suppose this root node dies off. In this case, automatically the next person will be this. Now there is a very interesting property. If I look at this particular node ID, this node ID's root node will be this guy. If this guy is root node, I have to figure out this will be this person. So it's going to be pretty simple that if I am the root node for a hash ID, I can now send a message, and this message I can call copy, and I can also even identify how many copies have to be created. I say there is already copy, so k minus 1 further have to be created. What will be the destination of this message? So destination of this message will be the root of R itself. This basically I should call it R0. And then whatever is the key value pair which I want to store, that will go. So this will be received by R1, which is the next guy. If this is the root node, so this is going to be received by this person, which is R1 now. So when R1 receives it, R1 will also now send the same message. It will keep the same copy. And it will say again it will be a copy, but now it will reduce the number. Further only k minus 2 copies need to be created. The destination where the message has to go has to be root of R1 now. So this interesting property that R first root is the root of R0. Okay, and similarly root of R1 will be R2, and so on. This property gets actually always exist in a chord system. So this is actually can be very easily done. So this way I can maintain k copies. Now what we can do is that each one of these entries, so you have one entry here, there will be now entries which are going to be created. So let k be equal to 4 in this case. There are 4 entries. So this guy is a root node. So all these guys also will keep on republishing the entry. So whenever they will republish the entry, it will always land up with this particular root node. So periodically they can all do it actually. Okay. So every time it comes here, the responsibility of this root node, whenever it gets a message, a republished thing, and there is a timer, before that it has to again send this copy message. So this overhead of the protocol will be required to maintain the k copies. The moment it dies off, so the queries will automatically come to this other node. So the queries will come to this particular node. So whenever these guys will be republishing, or this itself will be republishing, this will be coming back to again terminating to this particular node only. And suppose whenever this node comes back again, it is alive. So this republishing will be happening and will be terminating here, and then again it will create the k copies. So last guy who was the 4th copy will ultimately, it will not be receiving the republish. When the copies are being copy messages will not be received by this person, it will remove. So automatically whichever is the root, so next k nodes will always be holding on to the copy. So this is a very simple thing which can be done with chord algorithm. Now the question is this logic is also true for even other algorithms or not? Okay, for example, if for a hash ID, if I look at Tapestry for example, for a hash ID, if I find that there is going to be a root node is R, so if this guy dies off, for whatever values which it is holding, for those values will the root node will be the next person or not? In chord, this is always ensured. If this guy dies off, all the entries which is being held by this node, for those entries this person will be the root node. So in case of a tapestry or a pastry, will it be possible that if my root this R dies off, next, so whatever is the root node for this R0, so this is R1, will the R1 will be the root node for all the values held by R0? Actually, this is not true. This is only true for chord case, but not true for pastry or tapestry. So I can actually give very simple example for this and show that this actually is not possible in case of pastry or in case of tapestry both. Okay. So for example, in case of a tapestry, there is a nodes which are actually held in this fashion. So you have a hash ID which is going to come here. Okay. So in case of tapestry, it is always a closed numerical closeness. So this is the numerically closed thing. So this will be the root node. This will be R0. Okay. So next, we can actually figure out a node which is going to be closer. So I can just make some minor change here. And I can actually represent by a distance. So this is, for example, say 10 is the total distance here. So this is 8 and this is 2. Okay. So if I have a distance here which is going to be at say 9 distance away. This is 9 from this guy. So for this R0, the root node will be this person. But for hash ID, when this guy dies off, the root node will be, so when this person dies off, so from the hash ID, this will be 8 distance away and this will be 11 distance away. So this will be the root node. While for R0, this was the root node. So henceforth, the earlier logic which is true for chord is not true for pastry. Okay. So similarly, I can actually show that even for a tapestry algorithm, this will not be true. So let's take a case that there is a node called 0, 1, 2, 3. I am again taking a 4-digit system. And this has a table in its table 0, 1, 3, 0. It has 0, 1, 5, 4. It has 0, 1, 6, 0. Okay. And the hash ID which is in question with me is, which I am trying to search, is a 0, 1, 4, 1. Okay. So what will be happening in this case? So it will be now 0, 1, 4, 1. So 0, 1 matches. So it will actually search for this particular entry. This happens to be the third column, obviously. Okay, because 0, 1 is matching, this has to be third column. Only third entries are changing here. So it will now try to find out 3, 4, 5, 6. So it has to be this particular entry where the query has to be handed over. So it will come to 0, 1, 5, 4. So 0, 1, 5, 4. So 0, 1, 5, 4 will have an entry says 0, 1, 6, 2, 0, 1, 3, 0. That's a third column entry actually. Then it also can have, it may not have a fourth entry. There is no fourth entry in this case. Okay, so there is no entry with 0, 1, 5 onward, there is no entry. So when it will now search for this thing, it will find out it's actually the 4, the third digit here, lies between 3 and 5. So this itself should be a root node. The root node for 0, 1, 4, 1 will be 0, 1, 5, 4. Now 0, 1, 5, 4 dies actually. Then what is going to happen? Let's see. Okay. So 0, 1, 2, 3 contains the 0, 1, 5, 4. The 0, 1, 5, 4 is dead. Okay. So once this is dead, what will be the entry? There is no entry here. So it will now search for 3 and 6. So let me figure out what will be the root node for 0, 1, 5, 4. I need to find out for this first, whether the root node of 0, 1, 5, 4 will be the new root node of 0, 1, 4, 1. So when I look for 0, 1, 5, 4 in this new entry, so this entry is all gone. 0, 1, 5, 4 no more exists because it is dead. So 0, 1, 5, 4 when I will search, it will go to 0, 1, 6, 0. So 0, 1, 6, in fact I should call it 0, 1, 6, 2 in my example I have said. So I am going to keep it 0, 1, 6, 2. So 0, 1, 6, 2 if I create a table. So 0, 1, 6, 2 can have entry 0, 1, 2, 0, 0, 1, 3, 0 for example, it can be there. Okay. So in this case, it will find out that 0154, if it comes to 0162, this can further have an entry 01660169. So 0162, when we'll actually try to find out 0154, it will find that this actually matches it. This itself will be the root node responsible. So it has to move to the next column. And 0154, now 4 lies between 2 and 6. So it will be handed over to the query from here. From this 162 will come to all the way here. And this guy will be now handing over the query to 0166. So 0166 will become the root node, and it has an entry such that this the only where it will actually get terminated. So this will become the root node for 0154. Okay. While now look for what happens with 0141. So when 0141 will come here, it will also go to 0162. So once it goes to 0162, it will also reach here at the same place. So once it comes here 0141, so you will find out it comes to, it matches with 0162. Now when it looks at 0162, so it goes to the last one because there is no other entry here, and here where this one is going to match, so 0162 will be the root node in this case. So the root of 0141 will be 0162, while root of 0154 will be 0166. Because of the last digit variation, this is going to happen. So again, the same logic which was true in chord is not true in tapestry also. So I cannot use this method. So we have to now choose for some alternative approach. So alternative approach which can work even in other kind of DHT algorithms will be, one possibility is that your key value pair is actually sent to a root node. This R now has to now search for, from its own routing table, to find out some other nodes which can act as a backup. So it can create 2 backups. That is a possibility. That's one possibility, to create 2 parallel backups, and it will send the copies to them. So they will hold the copy. They will hold the copy actually, and their job is to continuously monitor R. So R is actually maintaining this key value pair here in its database, and mostly it will be serving with that. But B1 and B2 will periodically monitor if R is alive or not alive. The moment R is dead, they can't actually get a heartbeat from R. They will simply republish the entry. So same key value pair will be republished. And the moment this is republished, it will go to another root node, which is an alternative, which in turn will find out their own B1s and B2 backups, and they will be maintaining the copy and they will be monitoring. So now this entry should essentially, every time republish happen, this entry has to come back to the R. R in turn will actually can send this entry back here, or can reset the timer, expiry timer for B2 entry. So backup entries are going to expire and purged. Here key value pair, this back expiry is different. This will be again going to have the same flag f is equal to 0 or 1. Whether it's a final kind of expiry or it's a expiry will be reset up with every access, and then the expiry value which will be there. Okay, expiry timer maximum value. This is a fixed expiry which is going to expire when f is equal to 1, when it is final. This expiry value will always be reset whenever it's going to be accessed. Okay, so this is one way it can be done. Another alternative is that when the root node gets the information, it sends to the backup node and it tells him that you are the backup one, so it maintains the entry and it keeps on monitoring this guy. So whenever this guy fails, it will do the republish. B1 also finds out somebody and says that you are the backup for me. So they need to maintain, and this guy need to know where my backup is there actually. For this one, where is the backup? For every key value thing, it also now create a backup which guy is maintaining. So when this guy is going to maintain an entry for key value pair as a backup entry, it will also maintain where if there is a backup. So you can create any number of backups. The last guy will not in the table will have key value pairs, but the backup entry will be null in this case. So there is no more backup, only these are maintained. So each one of them is supposed to keep on monitoring R. So all of them are not going to fail, all of them are going to publish monitor R, and all of them are going to republish if the R fails. So the chances that all of these will fail is very low. So we can't give guarantee. We can only say probability that the things will be lost can be arbitrarily low. So lower the value you want for this probability of loss of key value pair. So the higher the number of replicas you need to create. So this is a serial parallel combination. This is serial combination which actually can be used. So this is how the resilience actually can get created. So, and of course, whenever the R's routing table is going to change and it can find out somebody else is going to be better root node, that will be happening because of the timer, republished timer, which is here. So remember, republished timer and expiry timer are two different things. Okay, there is also going to be a republished timer. So we should not confuse between these two. So R will actually keep on doing the republication. So if R actually finds out some other guy has become a better root node, so it will stop actually sending this, whenever this republished timer expires, it will not reset the timers with all these things. So they will automatically get purged, and this new root node has to now create its own backup chain. Okay, it will but retain value for some time before it actually purges the entry from here. In case it dies off, the request again will start coming in, so it need not learn again. So it will still maintain even after it is transferred the value, it will maintain it for some time for resilience purpose. So that's how essentially the resilience actually gets created. So far what we know is that DHT is actually works actually without any issue. Only problem is the resilience, which now we have created. Now in case of base DHT layer, normally this is not the issue. Base layer, normally you will be either maintaining user ID to node ID mapping. Okay, this will be again distally signed by user ID, so you will have a digital signatures. And the same user can be there on multiple nodes also, so there can be, you can actually put a certificate here, but we need not. Okay, digital signatures are good enough, and we can also now hold on to the user ID to certificate mapping for the user. Okay, so node ID can always, there is going to be a hash which is going to be, node ID actually is always a couplet where the public key of the node ID is the node ID. Public key part is actually signed by the corresponding private key. So signatures will be there. So this is what is going to be the total node ID. So this will ensure it's always randomly generated. Otherwise you can't generate this particular signed hash you will not be able to generate unless you have a corresponding private key. And if private and public key exist, they have to be randomly generated. So you cannot build a denial of service attack in this case. So this we had discussed earlier also. So only these two entries will be there. So roughly for each node, we have only two entries on an average. So in the base DHT, you will not be running out of memory because these are very small data structures, can be maintained by everybody. So you will never be running out of memory. But when we go to an application where, for example, I want to create a distributed file system. So every node is actually maintaining some storage where the file fragments are held for others. Okay, so every node does it. So every user can have this own file system space whose file fragments are stored in this DHT network. It's a DFS, we call it a storage DHT. The nodes which are participating in storage DHT, they can run short of space. Okay, now they are not doing only the base, in base layer like we had only two possible entries. They can have files, they can put movie, they can put all kind of stuff. So people can run out of space. So how to handle that situation where this is the root node for something, but it does not have a space. And since the root node is there, so queries will always come here. So it has to take help of other people to find out the storage and use it. But why somebody else is going to donate the storage? So I think the logical reason for this is if you donate the storage, chances are that you will get the storage should be higher. So it becomes a kind of a tit for tat mechanism, because of which the free riding will not be happening. Free riding implies that you don't want to share any storage of yours, but you take the storage of others. So we can avoid that. So in the next video, we will be looking at this particular algorithm, and we will start with the discussion on DFS and how this algorithm is actually can be built to ensure that there is no free riding in the system.